present any scientific news or some very sophisticated setups using pencil. A few weeks ago in Potsdam I was talking with Axel, and he told me that now the pencil code is able to do simulations also in cylindrical coordinates. A year before I was already using the pencil code in Cartesian coordinates for physical setups in a cylindrical enclosure, and it was working not very well. One had always the symmetry of the box in the magnetic field, so it was never axisymmetric. And now I saw a new chance to use the pencil code, and especially because it's available for using it in highly parallelized environments, getting huge resolution, and that's what I'm interested in doing simulations with really high Reynolds numbers, purely hydrodynamical, and in the next step then doing MRI simulations in comparison with some experiments, which might also be needing really high resolution. So that was the point. A few weeks ago I started with the cylindrical coordinates, and Axel also mentioned that it's not completely tested so far, and I started with the very basic tests one can do. So here I have my setup, a rotating annulus or Taylor-Fred system, where the inner and outer cylinder can rotate with different velocities. I describe it with the usual Reynolds number. I have the radius ratio, the height of the cylinder. And for these tests I was using an infinite cylinder, so with periodic boundary conditions in the z direction, as well as different profiles applied on the end caps. As I already said, cylindrical coordinates with pencil. It's nearly incompressible, so the maximum value of the velocity is around 1, and the speed of sound is set to 15, so the variation in the density is really low. It's isothermal, and I did several simulations in 2D as well as in 3D. So the first was to study the influence of the rotation rate of the outer cylinder. So I think everybody knows if the outer cylinder doesn't rotate, there's a critical Reynolds number around 70. For this one, that is using 30 grid points in the radial direction and 240 grid points in the axial direction. So gamma was 8, but I applied periodic boundary conditions. I found a critical Reynolds number of 72. And then I increased the rotation rate of the outer cylinder, and also the critical Reynolds number then increases, and everybody knows that the instability, so the onset of the Taylor vortices, cannot appear if one is beyond the Rayleigh criterion, and I think that's very good fulfilled. I ended here with a Reynolds number of 500. Everything else would make not so much sense with a two-dimensional one. And so I think for this first test, I would say the coordinates, the cylindrical setup is very well working. And I already said I'm interested in the high Reynolds number flows. The question here is, especially if one is looking at experiments where one has always solid end caps, what happens with the flow if the rotation rate is really large? So I'm talking about Reynolds numbers 10 to the 6, around that. So there were some first experiments in the last century, 1933, from Wendt, and he found instability for Reynolds number larger than 4 times 10 to the 4, maybe due to mechanical problems. There were experiments by Lathrop that found that the flow becomes unstable for Reynolds number probably larger than 10 to 5. And there is a numerical analysis what happens if one splits the end caps into several rings. So if one would use an infinite number of rings, one would have the correct profile, and there should be no influence from the end caps. And Hollerbach and Fournier showed that if one is using a finite number, 3, 4, 5 rings, or 10, then one has always such drops of the flow profile, so Stewartson layers that become thinner and thinner for growing Reynolds numbers. And so far, magnetorotational instability experiments with liquid metals that need such high Reynolds numbers, that the Ekman number corresponds to 1 over the Reynolds number, will never be possible. And there's another group that published in the end of the last year an article in Nature that they were able to get a stable flow, stable thread flow for Reynolds number of 10 to the 6, and everybody was a little bit surprised. And so perhaps what I have to tell also is that all these experiments talk about the thread flow beyond the value limit, so where it should be hydrodynamically stable. And what is more surprising here is that this Taylor thread system is really flat, so it's a wide gap, and the aspect ratio, so the height of the cylinder, is very low. So one would expect really a strong influence from the end caps, and the group of Fantoy were able to use a setup with only 2 rings, and so that's really surprisingly, and I want to at least try to do some numerical experiments to figure out if I can also find these Stewartson layers or if it's looking different. So that's why in the next steps I did not use an infinite cylinder but with finite end caps. First, as already said, infinite number of rings, then one should get the exact correct profile, and I have plotted here the theoretical profile and some profiles for several values of the z-axis, and it agrees perfectly. So if I would plot the difference between the mid-plane and the theoretical profile of the spherical correct profile, the difference is of the order of 10 to the minus 4. So it's really low. And in the next step, now I switched to these 2 different setups. First, one with 2 rings that the group of Antoine were using, and the 2 rings rotate independent from the inner and outer cylinder, and the angular velocities are 0.45 of the inner cylinder and 0.19 of the inner cylinder. The outer cylinder is rotating with 0.27, so the inner ring is a little bit slower than the inner cylinder. Sorry, the outer ring is a little bit slower than the outer cylinder. So, and the second setup is using the same setup Hollerbach and Fournier were using with 4 rings, where the inner and the outer rings are stick to the velocity of the inner and outer cylinder, and both others are in between. Okay, I have shown here the profiles of the U5 component of the velocity, and on the first glance one can see that here jet-like structure appears with a small feature here on the outside. We will see that it changes the profile, especially in the mid-plane here a little bit, and this profile has a strong influence from Ekman layers in the top and bottom regions.
How big is Ekman number? Oh, sorry.
This is for a Reynolds number of 1000.
So 10 to the minus 3.
10 to the minus 3.
Is it Z or
CR,
okay?
right?
Yeah.
It's axisymmetric, yeah.
All right.
Okay, and here are the profiles in the radial direction. Again, the solid line, it's the spherical correct profile, and one can see that all the profiles one gets with the steering setup are a little bit below the perfect crude flow, and the red dashed line, that's that one here on the inside, comes here the lowest one, and then even the slope changes and we get a minimum here, which one cannot really see on the measurements in this published paper. And with this four-ring setup, it looks a little bit smoother, but it's also not perfectly, and it's a little bit, or the velocities are always a little bit larger than the correct profile. This is for Reynolds 1000, and for 5000 it does not change dramatically, but these minima here becomes larger and larger. And so far I don't have really doubts that for Reynolds 10 to the 6 there's nothing happening here that makes the profile completely different. So that was only the pencil simulations, and in the next step I used the spectral element code from Fournier to compare pencil with these results I got from the spectral code. The profiles are shown here. I do not have an exact, cannot show exact the differences between these two results because it were different grids, and there was simply not enough time to do the work. But in principle one can see that the results are very similar, and yeah, and so far I think that at least the results of both codes for these pure hydrodynamic cases are more or less the same, and I would say that the hydrodynamic part of pencil for isothermal and nearly incompressible situations is working quite well, and axiometric. And the last thing I want to present, that's a result from the weekend, the first one with additional magnetic fields. That's the tailored Brett dynamo. There's a paper from Willis and Barengi, and they showed that if one starts with an already evolved tailored Brett flow, always two of these neighboring bolts are acting as a dynamo. And the Reynolds number is here roughly 2.5 times the critical Reynolds number, 102. Magnetic quantum number is 2. And I started the simulation pure hydrodynamical, and after the transition to the Taylor-Brett flow, I added some small random fluctuations to the magnetic field, and then one can see that the velocity drops down a little bit, and after a short decay time of the magnetic fluctuations, they start to grow, and after roughly 10 times of the viscous time scale, one reaches a steady state. And this is exactly the same that Willis and Barengi find. The next point is that this magnetic field as well as the velocity are non-axisymmetric. The velocity shows only even modes, and the magnetic field the odd modes. And if one compares then the energy of the largest part of the magnetic field with respect to the energy of the Taylor-Brett flow, then Willis and Barengi find that the magnetic field energy is of the order of 0.09 of the Taylor-Brett flow. My one with pencil showed 0.16, and also for the same with the spectral element code was also 0.16. So far the results of these both codes are exactly the same, and I think the difference here is due to boundary conditions. I use the normal field condition, and the spectral code from Willis and Barengi vacuum condition with an external potential. And okay, so the last point are plots of the magnetic field and velocity field. The second component, velocity u phi, here plotted in the R5 plane, so you can see it's not axisymmetric, and so from visually the m equal 2 mode might be dominating, but I think it's the axisymmetric, so m equal 0 and m equal 2 modes that are dominating. So I think one needs to further analyze by a simple Fourier decomposition. And the magnetic field, as expected, shows an m equal 1 symmetry. And the plots in the other direction, the Z plane, one can easily see the rolls of the Taylor system, the Taylor vortices, and in the magnetic field, that always two of these rolls together act as a small dynamo and producing a positive, negative, or vice versa, negative, positive part of the magnetic field. And so far, this first one really agrees with the results from Willis and Barengi, and I was really surprised that it's working. At least in the incompressible, nearly incompressible setup with isothermal conditions. So I think if there are problems, they might be related to some compressibility effects or thermal effects. That's the tests I've done so far, and the next step I hope to reach larger Reynolds number, and so far I'm really also interested in polarization in the x direction, because I think that would be helpful.
What? Polarization?
In the x direction. And then we will see what's the difference between the several numerical approaches, but I would expect that I get different results than Oliver and me. I don't know.
Thank you, very impressive. So I think so that was very impressive. And questions?
Your simulation are almost incompressible then.
Yes.
The sound speed is 15.
It's 15, and the maximum of the velocity is around 1. So the fluctuations in the density are of 10 to the minus 5, 10 to the minus 4.
Okay, and what the paper by the paper, the ANA paper that you...
From Willis and Barengi, it's also incompressible.
Okay.
Oh, it's really incompressible.
And nobody did that using a compressible